Hello, class 12th physics, chapter Semiconductors. Theory part मैं पिछले 2 लेक्चर्स में कवर कर चुका हूँ। इस समय ये कुछ क्वेश्चंस हैं जो प्रीवियसली बोर्ड एग्ज़ाम्स में आए हैं, या तो मैंने उन्हें डायरेक्टली यहाँ इंक्लूड किया है या उन क्वेश्चन को थोड़ा सा मॉडिफिकेशन के साथ यहाँ इंक्लूड किया है। So let's begin. What happens to width of depletion layer of a PN junction when it is forward bias, reverse bias? Shortcut answer, forward bias में depletion layer की width thin हो जाएगी और यहाँ thick हो जाएगी। तो दैट्स ऑल द आंसर। लेकिन थोड़ा सा अगर एक्सप्लेन करना चाहें तो ए पार्ट एज मेजॉरिटी चार्ज कैरियर्स in a greater amount, मैं शॉर्ट फॉर्म में लिख रहा हूं तो आप समझ लीजिएगा, इसीलिए मैं साथ में बोल भी रहा हूं। ड्रिफ्ट टुवर्ड द जंक्शन so width of depletion layer decreases. B, B part reverse bias में as majority charge carriers moves away from the junction so width of depletion layer increases. However, there are minority charge carriers but their movement in the depletion layer, in the depletion region is negligible. So the idea is majority charge carriers move toward the junction, so depletion region become thinner, width of depletion layer decreases. In reverse bias they move away, so that's why width of depletion layer increases. There is a thing that these minority charge carriers are moving, but they are very few, so their effect can be neglected. Next question, what is the difference between p-type and n-type semiconductors? It is better to do this kind of difference between them. So we can say p-type semiconductor is obtained. You can write entire this, I am just writing it, the bullet point of it. P-type semiconductor is obtained is obtained by doping an intrinsic semiconductor with a 13 group impurity. 13 group impurity, also called acceptor impurity. Why it is called so? Think about it. In the upcoming questions, we will cover this thing also. Here, N-type semiconductor is obtained by doping 15th group impurity which is also called donor impurity. To intrinsic semiconductor. One more difference is there. In p-type semiconductor, holes are majority charge carriers. So number of holes per unit volume is very greater than number of free electron per unit volume. In the same way, in n-type semiconductor, free electrons are the majority charge carriers. So number of free electrons is very greater than number of holes per unit volume. P-type semiconductor, if doping for same doping, same amount of doping, conductivity in p-type semiconductor is lesser. Conductivity in n-type semiconductor is more. Why is it so? It is because mobility of free electrons is greater than, remember this thing, it can be used somewhere else. Mobility of electrons is greater than mobility of holes. This is an additional information, and due to which n-type is more conducting. Next, one more difference can be there, that in p-type semiconductor, when we draw its energy band diagram, then its valence band get broadened because of addition of additional energy level of holes. And here in n-type semiconductor, conduction band gets broader by the addition of an extra energy level of donor impurity. Okay, anytime it is shown like this. So there are so many differences now. Actually only 2 is required because it was carrying 2 marks. So next, distinguish between intrinsic and a p-type semiconductor. Is there any net positive charge on p-type semiconductor? No. Why or why not? Alright, so distinguish between intrinsic and p-type semiconductor. So once again we can differentiate like this. Intrinsic, it is pure semiconductor. A pure semiconductor is called an intrinsic semiconductor, and p-type semiconductor, so I can pick the information from here. It is obtained by doping of 13 group impurity into an intrinsic semiconductor. Other differences are here number of free electrons is equal to number of holes per unit volume, and here holes are majority charge carriers, so number of holes is very greater than number of free electrons. Energy band, according to energy band diagram, there is simply two energy levels. Here is valency band, conduction band, so its energy gap, it has lesser energy gap because its valence band get broadened, so energy gap is lesser. Alright, so these are the three differences. Four difference can also be there, that its conductivity is lesser. This time there's no explanation like this. It's lesser and it's more. Why is it so? Because it is intrinsic semiconductor, and when it becomes p-type, then actually it is we desirably make it p-type so that its conductivity should increase, so that is why here conductivity is more. So same question can be asked with intrinsic and n-type, so you can take these value in contrast to this. So is there any net positive charge in p-type semiconductor? So its answer is this is the first part of the question. Second part is no, because holes formed there as one of the bond by acceptor impurity does not form. Impurity atom does not form. So it is not like that atom is losing something or gaining something. So all the atoms are still having equal positive and negative charges. So this is the reason there is no gain or loss of charge. Charge by the crystal. Okay, now there is a circuit. We haven't seen such kind of circuit in the entire discussion of semiconductor chapter, but here we have something. So many students can think about drawing of their characteristic curves, but it is not that. Find the current through each branch in the adjacent circuit. So each branch means here, here, and here. So these are the we can do one thing. We can mark this current as I1, this current as I2, and this current as I3. Okay, so many of you might be thinking that Kirchhoff law will be applied here, but no. Actually, as there is no information about these diodes is given, so we will consider both diode as ideal diode. So the solution is, since an ideal diode, actually they haven't said about this, but if they haven't given, so we will consider it as an ideal diode. An ideal diode offers zero resistance in forward bias and infinite in reverse bias. So we will redraw the circuit. So given circuit can be redrawn as actually that diode is not offering any resistance, so we can consider it as a simple wire, and I am just removing this branch because here diode is in reverse bias, so it will have infinite resistance, no current will pass through it. So now there are only two resistance now, 2 ohm, 1 ohm. This is 6 volt. So now there's no need to write them I1 and I3 because both are same, I1 equal to I3. So now I will not write them I1, I3, I will write them simply I. Okay, so there are two resistance which are in series, so we can directly do this. We don't have to explain the things here. So V equal to I 2 plus 1, or if you think it is we are skipping so many terms, so I can do it like this. So V is 6, I is I, 2 plus 1, that is 3, 3I. So I equal to 6 by 3, that is 2 ampere. And that's all. So I1 equal to 2, I3 equal to 2 ampere, and we know that I2, which we have chosen, is 0. Identify device X in the following diagram and write its working. So you can see actually in entire physics we have seen such kind of diagram as half wave rectifier. So the answer is X is a half wave rectifier. And now we have to write its working. So in the notes I have covered this thing up, so I'm just briefly telling you. I'm not stating the answer, you know. So here what you have to do, you have to draw this diagram, and you have to put a heading for this. I have just left no space for that, so I'm writing it here for first half cycle. So for first half cycle, this is A, this is B. A is at positive potential, B is at negative potential, and this is RL. So this is input, and this is output. So you can write like during first half cycle, A is at positive potential, B is at negative potential, so diode gets forward biased, and that positive peak occurs obtained at the output. And during negative half cycle, during second half cycle, for first half cycle, for second half cycle. Now what happens, we have to once again draw it like this. Okay, sometime people also ask that what is the principle of this device. So it is based upon the working of PN junction diode, which offers negligible resistance in forward bias. If we talk about ideal diode, okay, so it offers no resistance in forward bias and infinite resistance in reverse bias. This is the principle. Actually it does not happen, but in principle this is what happens. This is what assumed. So there is RL, load resistance. Now in second half cycle, that is negative cycle, so this, it was for the positive which we have taken earlier, and this is negative half cycle. So in this case, A is at negative potential and B is at positive potential, so diode get reverse biased, and diode get reverse biased, so no current is obtained in the output, a gap. So finally this AC gets converted, this was the overall input, so it gets converted into this type of one directional current, and as it is one directional, so it is a fluctuating DC. Further, they can ask how can we remove those fluctuations. So by the use of filter circuit which has diode in parallel or inductor in series or combination of both. So I'm not going into the working of that filter circuit, enough here. Okay, next with the help of circuit diagram, distinguish between forward and reverse biasing. All right, very less space is there, so I'm dividing one half and again half. So circuit diagram, here for forward bias, here for reverse bias. So in forward bias, you need to write one liner for both of them. Help of circuit diagram, distinguish between forward and reverse. So no need to explain about their working. So there are two diagrams for forward bias and reverse bias here, this one and this one. If we want to explain the working of forward bias, then we have to draw both of these diagram. But if they ask for distinguish between, then we can just draw these two circuit diagrams here. So in forward bias, this is the PN junction diode, and here positive to positive, and here we will connect an emitter and a voltmeter in parallel to this. And one more thing, rheostat, by which we are varying voltage and hence current is also varying. So in the same way, reverse bias. Now what is happening? Polarity is reversed. You can see sometime I mark arrow here and sometime there, so it doesn't matter. But why I do this? Because I just point out this arrow along the direction of current, so that is why. Now here V volt, and this is microammeter. Actually it is milliammeter. Okay, so now there draw there with the help of circuit diagram, distinguish between forward bias and reverse bias. So you can directly write that for forward bias, positive p-type region of semiconductor PN diode is connected to positive terminal, and n-type region is connected to negative terminal, and opposite to that in reverse bias, because they have asked for in terms of circuit diagram only. Now draw their characteristics. So we can do this in a single graph. This is for forward bias, I V, it is in milliampere, and here once again V, and this is I, it is in microampere. So this is how graph goes, and they didn't ask for any other points in the graph, but yeah, of course, if we know, we can mark these points. This is VK, that is knee voltage, and here not exactly like this, give a slight reading here like this, and then it will drop. So this is VB, breakdown voltage, avalanche breakdown voltage also called. Okay, so in why current in reverse bias is always almost independent of voltage. If you want to answer it of your own, pause the video and guess the answer. Okay, now I am telling you. So in reverse bias, actually in reverse bias, minority charge carriers are responsible for current. So responsible for current which are limited in quantity. Therefore अब सब कुछ क्वेश्चन से आ जाएगा. Current in reverse bias is almost independent of voltage. In very easy words, जब रिवर्स बायस में उतने चार्ज कैरियर्स हैं ही नहीं, तो हाई वोल्टेज जब हम अप्लाई करेंगे देन ऑल ऑफ द चार्ज कैरियर्स विल गेट यूज्ड अप। और वोल्टेज कितनी भी बढ़ा लो, जब वो हैं ही नहीं, चार्ज कैरियर्स लिमिटेड हैं, तो हाउ कैन दे कंट्रीब्यूट टू करंट? जितने हैं उतने ही फ्लो होते रहेंगे। सो दैट इज़ वाई it is almost independent to voltage. Now draw a labeled diagram of full wave rectifier, state its working principle, show the input output waveform. So working principle, as I stated earlier, that an ideal diode offers zero resistance in forward bias and infinite resistance in reverse bias. This is the principle of that full wave rectifier. Full as well as for half, the same principle works. So its circuit diagram: first there is a step down transformer, a center tabbed step down transformer. This transformer is called center tabbed. Center tabbed step down transformer. From here we have just shown that these two wires, we are taking output from these two wires. So this is D1, this is D2, A, B. In fact, A, B, C, that will be fine. So once again, during positive half cycle, during first half cycle, A is at positive potential, C is at negative potential. So what happens, D1 get forward bias and D2 get reverse biased. So D1 conducts and positive peak occurs at the output. This is input, this is output. And during second half cycle, what happens, D1, D2, A is at negative potential and C is at positive potential. So D2 gets forward biased and D1 get reverse biased. Now D2 will conduct, and remember this thing, D2 is in the circuit having 180-degree phase shift. So it flows the current in the same direction that was flown from the D1. The direction in which current flown from the D1. So this was the direction. This time this is the earlier this was the direction. So this time D1 will not conduct, D2 will conduct. So this will be the direction. So direction is same in both the cases. So how can we represent it? So this is input, and because of 180 phase shift, this will be come out as positive cycle. So overall, if this is how input signal, input AC is there, so after rectification only positive peaks will be there. That's it. Input, output. So this is the question we didn't quite covered in the lecture, but such kind of question can be asked. Draw energy band diagram of n-type and p-type semiconductors at room temperature at 0 Kelvin. So it is quite annoying that how can we know, and the diagram, band diagram, which we studied in the lecture. So what was that? Was it at room temperature or at 0 Kelvin? So remember one thing, that at 0 Kelvin, first I am drawing at 0 Kelvin, B part first. So it's looking like okay, it is 0 Kelvin. So for n-type, this is the valence band, sorry, conduction band. This is the valence band. And at 0 Kelvin, valence band is completely filled and conduction band is completely empty. Filled, it is empty completely. Okay, so you can state here, we have to draw only. So but if explanation is asked, then you can say that at 0 Kelvin, conduction band is completely empty and valence band is completely filled. Remember one thing, at 0 Kelvin, semiconductor acts as an insulator, perfect insulator. Now in p-type, oh sorry, one thing I have missed. Why is it n-type? Because of so for n-type semiconductor, this conduction band get broadened due to an extra energy level, and there free electron resides, and that's it. At 0 Kelvin, nothing extra, no electron, electron from valence band can jump to a conduction band. And in the same way, p-type semiconductor, this is conduction band, this is valence band, and valence band get broadened, and there are holes. So once again, conduction band is totally empty, completely empty, and it is completely filled. And additionally, in addition, there is an extra energy level of these acceptor impurities. So at 0 Kelvin, both n-type and p-type has zero conductivity. They do not conduct. Okay. Now, which will have greater conductivity? So at 0 Kelvin, both have zero conductivity. Both have zero conductivity. This is a symbol for conductivity. Actually, I did something wrong. I have to draw it here and p-type here. But anyway, because lots of space will be wasted. Anyway, at room temperature, Don't do like as I did. First I did B, then A, just in order to make you understand. Otherwise, in the exam, these subparts should be done in order, just to be in at the safer side. Actually, no one is going to, deduct your marks. Okay, at room temperature, this is also given as T greater than 0 Kelvin. So now what will happen? And this is what the general case is. So here there is valence band, there is conduction band. So at room temperature, it is possible that some of the electron can jump into this conduction band. So we can draw few extra electrons here, and in the same amount holes there in valence band, and that's all. And in p-type semiconductor, once again there is conduction band, valence band, broadening due to acceptor region, and few of the electron can jump here as usual, leaving few more holes there in valence band. And here the conductivity, sigma for conductivity, you need to write. I am just using symbols. Conductivity of n-type semiconductor is greater than conductivity of p-type semiconductor because of mobility of electrons. Alright, so next, this was a silly question. Identify biasing in following. Positive is connected to positive, it is forward bias. Negative connected to positive, for reverse bias. Okay, so what's important in this question? What happens actually? This symbol. What is this? We know this, but we don't know this. Actually, whenever if there is a resistor and an arrow is marked over it, it means it is a variable resistor. In the same way, if you see this, it is capacitor. Actually, it is a variable capacitor. So in the same way, it is variable cell. It means there is some arrangement by which we can vary voltage applied across the cell. Alright, which of the following is forward bias and why? Actually, forward bias, generally we think that this positive terminal should be connected to positive and this negative should be connected to negative. No, actually this is not the complete explanation for this. Forward bias means this P region must be connected to higher potential and this terminal should be connected to lower potential. And here P is connected to 0 volt. This is earthing, means 0 volt, and this negative is connected to positive, that is higher. This is low, this is high. So this was for forward bias. So this time situation is reversed. So it is reverse bias. Here -5, -10. So -5 is at higher potential. This is lower. So this is forward bias. Here it is -5, it is 0. So it is high, it is low, and hence it is reverse biased. Here it is connected to positive, high, low, so it is forward bias. That's all. In the given diagram, which bulb out of B1 or B2 will glow and why? There is a cell battery, so current will go this way and that way. So, oh god, I haven't written B1 and B2. So this is B1, this is B2. I'm marking diode D1 and diode D2. So for B2 circuit, a B2 loop, we can say, D2 gets reverse biased. So no current flows in that loop. Oh, too many O. So B2 will not glow. Okay. For B1 circuit, D1 gets forward bias. So current flows through B1 and it glows. So the answer is B1. Well, I'm going from 14, then 13, then 12. I want to spend more time with this question. Describe two important processes when p-n junction just formed. So actually in my lecture, as I remember, I told you about that, but didn't use that term. The two different processes are, I'm not distinguishing between them, I'm just explaining, describing them, both of them. So that is why I have made these two columns in order to list down them, not bringing out their differences, just telling those two processes. First process is diffusion and second is drift. Actually drift take place when potential difference is applied, but before that still it is applied. So diffusion, so when pn diode PN junction formed due to diffusion electron hole recombination takes place leaving positive ion on N side near the junction and negative ion on P side near the junction. So this is diffusion due to diffusion, and diffusion takes place because difference in concentration. Difference in concentration of holes and electron in P and N region respectively. Now drift. Okay. After diffusion, a depletion layer is formed. By positive ions and negative ions. In N and P regions respectively near the junction. Due to electric field produced by opposite charged ions charge carriers drift away from the junction. toward their respective regions. Toward respective regions. What are these respective regions? That is, holes go back to P region and electron go back to N region. So what happens actually when p-n junction is formed, then diffusion takes place because of difference in concentration, forming a depletion layer. Depletion layer has two oppositely charged ionic layer, and as this layer formed, then further diffusion of electron get drifted. These are drifted back. These holes are drifted back. So because there is an electric field here, so negative charge cannot move along the electric field. It will move back, and hence, and in the same way, hole also. Identify adjacent circuit arrangement and draw schematic input-output waveform. So this is actually full wave rectifier circuit. We draw it in different way, in a convenient way. This is how we draw it. This is the convenient diagram for full wave rectifier, but in the book this is the diagram, so keep this in your mind, because sometimes this can be asked, this can be shown in the question, and you might not be identifying this. So it is the same diagram as we have drawn earlier. So this is full wave rectifier, and schematic input output. So in any way you can draw it. I'm drawing it like this. This is input, and just below this I'm drawing this. This is output. Alright, so finally this one. Very nice question. So happy to see this kind of question. I wasn't thinking a question like this. In the given circuit diagram, S is a semiconductor. Would you increase or decrease value of R? R is a variable resistor. To keep reading of emitter constant when S is heated. So many things are there. There is a variable resistor. There is heating of S. S is semiconductor, and there is an emitter, and we need to keep its current constant. So why should we keep its current constant? Isn't it constant? So first step, why current is not constant when it is being heated? So we know when semiconductor is heated, that is, for semiconductor, if temperature increases, then its resistivity decreases. This is for semiconductor. Same kind of question can be asked for a metal. if it is being heated. So same question can be asked in that way also. So here semiconductor is being heated, so its resistivity will be decreasing, that is its resistance. I'm marking it as R dash, don't get confused with this. Its resistance is R dash or R subscript S. It should also be decreasing, and if RS is decreasing, it means current is increasing. So to keep current down, we have to increase the resistance. So we have to increase the resistance R. Now we will go step by step. When semiconductor S is heated, its temperature increases. Since it is semiconductor, so its resistivity decreases. So resistance of S decreases. To okay, as resistance of S is decreasing, to balance this decrease, R should be increased. To keep current constant. You can see it's not a big question, but I don't know of how much marks it was carrying, but I believe that this type of question must carry 3 marks. Very good, very thought-provoking question. Next question, how does energy band for pure semiconductor affected when this semiconductor is doped with acceptor impurity, donor impurity? So pure semiconductor, this is the energy band diagram for it. Okay. Next, for doped with, I'm putting A, doped with acceptor impurities. Acceptor impurities means 13th group impurity. So there will be an addition of band in valence band region. We can say it acceptor energy level is added, and in the same way here donor impurity level is added. That's all. Why gallium arsenide is most commonly used in making solar cell? So actually we don't know gallium arsenide is used, but we know that fabrication of solar cell requires 2 things. First, higher optical absorption. Second, higher conductivity. So we can say that gallium arsenide is used because it has higher optical absorption and higher conductivity. Why should photodiode be operated at reverse bias? So when photodiode is exposed to light, large number of electron hole generated. They are released. Released is quite okay. Released. All right. Which are very, very greater than number of minority charge. So it can be effectively observed in reverse bias, but not in forward bias, as those released electron holes are very, very less than majority charge carriers. Which contribute in forward bias. So actually the number of electron hole generated when exposed to light are not much so that it could influence forward current, but they give a greater addition in reverse current. So that is why it is operated in reverse bias. What is the function of photodiode? So answer is here. When photodiode is exposed to light, large number of electron hole pair released. So I'm connecting it here. So its conductivity decreases. So it is useful in photodetectors, that is light sensors. photodetector, light sensor. And also it is also used as a glow detector, that how much a person's skin is glowing and all that. Show variation of resistivity of silicon with temperature. Well, this question is related to current electricity chapter, but people might be get confused about this. So this is actually related to current electricity. There are several graphs of copper and silicon and all that. So the variation of resistivity with time, with temperature, is like this. We know that at 0 Kelvin resistivity is very high, so almost it acts as insulator, so very high resistivity. But as temperature increases, resistivity decreases in inverse proportion. That is why it is a graph with slight curve. Draw current versus voltage for solar cell. Okay, so for solar cell, actually the typical graph is this. That's all. This current is called short circuit current, and this voltage is called open circuit voltage. So draw circuit diagram for illuminated photodiode in reverse bias. Actually, yeah, illuminated photodiode, there's no use to draw photodiode to connect photodiode in forward bias, so it is always connected in reverse bias. You can connect it in forward bias, but there's no use for that. So it will be connected in reverse bias. You can apply some rheostat here, and this is the circuit for that. We will measure current by using some microammeter, and a potential difference can also be measured. So this is V. And how photodiode is used to measure intensity of light. So we will measure current, and with the increase in current, we can estimate the intensity of light. So both are directly proportional. Intensity of light is directly proportional to reverse current. Actually, a part of a fraction of that current is due to the minority charge carriers, but greater amount is because of the incident um, light on that photodiode. Mention the important consideration required while fabrication of LED photodiode solar cell. Draw characteristic of each. So for LED, we require the material, suitable material, for desired color, for light for light of suitable color. Photodiode, material having band gap forbidden gap, forbidden energy actually. Gap energy equivalent to energy of photon, energy of visible EMW. So the band gap, we have to choose material in such a way so that the band gap between conduction band and valence band for that has the energy same as the energy of visible part of electromagnetic waves. Alright, so last solar cell as discussed earlier, high optical absorption and high conductivity. What is dark current in photodiode? When the reverse bias current flowing through photodiode when no light is incident on it. So it means this VI when illuminated means when light is incident on it, then this is the reverse current, and when no light, then this is the current. So that's all the collection I have made, and if you people think that there are some questions which are essential and which are not covered in the lecture I had given and in these questions, so you can write me in the comment, and I hope these questions were thought-provoking and a very good tool for the revision. Okay, so bye bye, see you in the next video.